So this is Math 145, Section 6.2 notes. What we did in Section 6.1 started us on this exploration of discrete random variables. In 6.2, we look at a very specific discrete random variable called the binomial probability distribution. Think about this. Toss 10 coins. This is my thought bubble. What's the probability that we get exactly 7 heads, or maybe less than 5 heads, or anything, right? What's the probability I get between 4 and 8 heads? Those are the kinds of questions that we're going to answer here. And so the very first thing we do is we define an experiment to be a binomial experiment if it fits all 4 of these criteria. Go ahead and read them over. You can pause me here, and then we'll talk. So we're going to look at experiments being asked to find probabilities of binomial experiments. But first, of course, you have to determine if something is a binomial experiment. And so this definition helps you out. Basically sets out 4 things that's got to be true. And all 4 things have got to be true about your experiment that you're dealing with. Number 1, the experiment is performed a fixed number of times. Each time you do the experiment is called a trial. Now think about it. If I say, as in my thought bubble here, toss 10 coins, what's the probability, blah, 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 blah? That is 10 trials, isn't it? Okay, number 2, the trials are independent. Remember what independence means. We saw that phrase back in chapter 5. This means that the outcome of one trial will not affect the outcome of the other trials. And that is true when I toss 10 coins, isn't it? Okay, perfect. Number 3. For each trial, there are 2 mutually exclusive outcomes. Think about that. When I toss 10 coins, I either get a head or not a head, right? Or tail, right? So it's a success or a failure. And we want to think about the thing that I'm asking about the probability of. For instance, in my thought bubble, the probability of getting exactly 7 heads. That head on a toss of a coin is called a success. Okay? And number 4 criteria to be a binomial experiment is that the probability of success is fixed for each trial. It does not change as you progress through the experiment. So again, if you toss 10 coins, the probability that the first one is a heads is exactly the same for the probability that the second one is a head, or the third one is a head, and the blah, 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 blah. Okay? Now, we have a little bit of notation. You're going to talk about n, lowercase n, independent trials. We're going to call that probability of success, P. And since failure is the only other option, 1 minus P would be the probability of failure, wouldn't it? And then we're also going to reintroduce the idea that you're going to call the random variable capital X. What X will do is counts how many successes we get out of n trials. So X ranges from 0 to n. X being the possible number of successes you could get, meaning if I toss 10 coins, X is going to count how many heads did I get out of those 10 trials. Number 1 asks you to determine if each of those 3 situations is in fact a binomial experiment. Go through each of those 4 criteria and see if they fit for A, B, and C. And go ahead and pause me now, and then we'll get back together. And also, you'll notice that it tells you if it is a binomial experiment, give the values of NP and possible values that X could take on. Okay? So for part A, a football kicker attempts 10 kicks through the uprights. The probability that he makes any one kick is 75%. The number of kicks out of 10 is recorded. And so I'm thinking about how, going back up to these criteria up here, I'm thinking about how the experiment is performed a fixed number of times, right? He's going to attempt 10 kicks. The trials are independent. We're going to assume that he's not going to go on a streak or get upset that he missed the first one and so he messes up the second one. Nothing like that, right? There's no indication of that. So we're going to say that the trials are in fact independent. Are there 2 mutually exclusive outcomes? Why, yes, there are. There's make the kick or not make the kick, right? Excuse me. And number 4, the probability of success is fixed for each trial of the experiment. And it's absolutely true because, again, they're not telling us that If he misses one, he gets more anxious and he can't make the next one as well. There's nothing like that. It's simply the probability that he makes any one kick is 75%, and that's that fixed probability of success we're looking for. So I say yes, it is in fact a binomial experiment, and I've got the number of trials being 10, the probability of success being 0.75, and X taking on values from 0 through 10, right? Again, the possible outcomes for counting the number of successful kicks. And actually, I meant to rewrite this, but what this really means is successful kicks. The number of successful kicks out of 10 is recorded. So I'm sorry about that. Go ahead and do B and C, and again, pause me down, and then we'll get back together. All right, to finish this out, part B. A bag has 10 marbles, including 3 red, 3 blue, and 4 yellow. A marble is chosen with replacement, and the color is recorded. This is not a binomial experiment. First of all, notice they didn't tell us how many times they were going to pick out a marble, right? First thing, they didn't even tell us a fixed number of trials, okay? The trials would be independent because they are replacing the marble, so criteria 2 could be met. But if you look at criteria 3, it says there's 2 mutually exclusive outcomes, success and failure, and there's clearly 3 things that could come out from this bag. And so there's just not only 2 outcomes, there's 3, right? So if any one of those criteria is not met, you say it's not a binomial experiment. So we can pretty much quit here and say, no, it's not a binomial experiment. Let's look at C. A survey revealed that 28% of Americans choose chocolate as their favorite ice cream. A sample of size 100 is obtained, and the number of respondents who chose chocolate is recorded. Think about this. I've got 100 trials, right? Each person I ask is a trial of my experiment. The probability of success, being that person says chocolate is their favorite, is 0.28. And the number of people who say chocolate is their favorite would range from 0 to 100. And so, in fact, I have, let's say that they're independent as well. That's criteria number 2, because it's a survey, right? We're randomly picking people. So we're going to say that's a binomial experiment. We looked at this setup for number 2 in section 6.1, so we have a little bit of familiarity with it. And back in 5.4, we drew a tree diagram. So hopefully you're a little familiar with the structure of this tree diagram. Go ahead and read it over, and then read over 2 and letter A there, and come back to me. Okay, let's look at the setup really quickly. First of all, we notice that it is a binomial experiment. Let's go through those criteria. It's telling us that they're going to randomly select 3 people for a sample. That is telling us there are 3 trials of this experiment. Are they independent? Why, yes, they are. That's criteria number 2 on page 1 of these notes. Yes, they're independent because it's a random sample, right? We've already discussed that as far as sampling goes. Number 3 criteria, for each trial, there are 2 mutually exclusive outcomes, success and failure. And think about this, the number of people in the sample with O negative blood is recorded. So X are the number of people that have O negative blood in our sample. And either a person has O negative blood or does not. So that's our success and failure. And then criteria number 4, the probability of success is fixed for each trial of the experiment. And that's exactly what that 7% of people in the U.S. have the blood type O negative is telling us. That P, let's write that as P, is 0.07. Okay, now I go to my tree diagram, and it says on part A, it says consult the tree diagram, which shows the possible outcomes for a sample of size 3. I used O and N as O negative and not O negative, and you'll see those throughout the diagram. We can assume independence, so we get the probabilities of each outcome by multiplying the probabilities along each branch. So let's go, we'll just follow one of these branches so you can see that. Excuse me. So let's say the first person is O negative with a probability of 0.07. let's say the second person happened to be not O negative with a probability of 0.93, right? Remember that was just 1 minus 0.07. That is the probability of failure. That's what we call that. Okay, and then let's say the third person happens to be O negative with a probability of 0.07. Again, that would be the outcome O and O, meaning the first person was O negative, the second person was not, the third person was O negative. How do I find that probability? I multiply those probabilities together. So I got 0.07 times 0.93 times 0.07, which turns out to be 0.004557. Okay? So that is our tree diagram. You will notice that I have the 8 possibilities here that could happen for these 3 people, any of which could be O negative. In part B, they want me to use the tree diagram to determine the value of X for each outcome and record it next to the diagram in the space provided. Remember, X is supposed to count the number of O negative people in each sample of 3. So let's go up here. For the outcome O, that means all 3 people were O negative. Therefore, X is 3. It's that simple. That's all I'm doing. I'm counting the number of O's there. In the second outcome, OON, 2 people. ONO, 2 people. Yeah, you get that? ONN, how many people in that outcome were O negative? Well, 1. And continuing, I am simply counting the number of O's in those guys. Now, what that allows me to do is part C. I'm going to find the probabilities by adding the probabilities above to fill in the probability distribution. So simply put, these 8 things, OOO, OON, ONO, etc., are the only 8 things that can occur. You will notice only one of those outcomes, being NNN, have no people with O negative blood or an X value of 0. So what's the probability that X is 0? Well, wouldn't it just be that probability? And in fact, it is. I'm going to throw that in there. Okay. Now, what's the probability? This is probability of that X is 1, which is again the probability that exactly 1 out of 3 people have O negative blood. Okay, let's see. Let's look at that. I'm going to do that one in red. Let's go up here. I'm looking for X values of 1, but look at that. There's more than one possibility, isn't there? So you'll notice all those probabilities are actually the exact same, 0.060543. I'm going to say either this happens, or this happens, or this happens. So add up those probabilities. So that is that thing plus itself 3 times. I got 0.181629. And I just didn't feel like it was necessary to round. I'm just going to leave my whole of it up there. Go ahead and fill in for the X values of 2 and 3 and come back to me when you're done with that. Okay, so I did the exact same thing that I just did for the X value of 1. For the X value of 2, it looked like there were 3 outcomes that had an X value of 2, so I added up those probabilities, and I got 0.013671. And then you notice how when X is 3, there's only one outcome for that, and so I just copied that probability down. Now, there is another way to find these probabilities, luckily, right? Because you wouldn't want to have to make a tree diagram for every possibility. And think about it. If you had a sample of 20 people, it would be almost impossible to physically draw that tree diagram. So we have to have another way. And here's our other way. Here is our formula that will find these probabilities. There's our definition right here. All right, so it says the probability of obtaining X successes in N independent trials of a binomial experiment is given by this guy here, this lovely little formula, where x can be any whole number from 0 to n, as we saw. Here, remember, p is the probability of success. Remember, before using this formula, you have to be sure that you're actually dealing with a binomial experiment. Okay, we did see this NCX before in section 5.5. That is why we did section 5.5. So it wouldn't be completely foreign to us when we came to it here. Let's do number 3 together. Use this formula to find P of 2 for the previous experiment about blood type. It should match what we got on the last page. Let's do it. I have my formula, which is this. I, of course, am just copying it down. I like to do that. And then let's do it. P of 2. Put your 2 in for x. Now, n was the number of trials, right, which was the number of people in our sample, which was 3. So I've got 3 choose 2 times p, the probability of success. Remember, that was the probability of any one person being O negative. That's 0.07. And I'm gonna raise that to x. So x is 2. Now I got 1 minus 0.07 raised to n minus x. And again, n was 3, x is 2, so 3 minus 2 gives me 1. Okay, now you do your 3 choose 2 on your calculator. Go ahead and do that, and you're going to get, you should get, what we got back on part C. Okay, so that is my calculator screen, and of course my answer there. What I did give you there was 2 different possibilities. The first one is technically what I put in. That's what I would normally put in. I did 1 minus 0.07 in my head and got 0.93, and that's where that 0.93 comes from. Just to show you that you don't need to do that in your head. If you want, you could in fact do it this way. In fact, I even raise that to 1 just to show you that you could in fact, do that thing on the calculator exactly kind of as the formula shows you. Just put that puppy in. Okay, you will notice that that is in fact the probability that we got for the x value of 2 on the last page. Now, you will see many problems that involve at least or no more than. You got to know what those mean. I did include some math symbols and some popular phrases they like to use in case you need to review that. Let's look at number 4. Go ahead and do number 4A and pause me down, and then we'll get back together. Okay, here is my work. Let's go over it. It says, according to the air travel consumer report, the 11 largest air carriers had an on-time percentage of 79%. Suppose that 10 flights are randomly selected and the number of on-time flights X is recorded. So I wrote down my general bits of information. I know N is 10, the number of trials. I know P is the probability of success is 0.79. Now let's think about this. If X is the number of on-time flights, then this 79% is my probability of success. X here would range from 0 through 10, being the number of flights in this sample that were on time. So part A says, what's the probability that there were 7 on-time flights out of the 10 surveyed? Which again means 3 of them were not on time. So we're thinking about 7 successes, that's this bit of our formula, and 3 failures, that's that bit of the formula. And then you've got to basically arrange those 7 successes in the 10 flights. And that's what that 10 choose 7 does for us. If you do that, and I show my calculator screen here, you get 0.213 about, which is 21.3% of samples of size 10 have 7 on-time flights. And you'll notice also when I did 1 minus 0.79 on my calculator, I did that 1 minus 0.7 in my head, got 0.21, and then raised that to 3 on the calculator. It just is a little easier to do that than have to do all the button pushing that the alternative would require. All right, number 4, we're just continuing with number 4B there. Same setup exactly. Again, remember P was 0.79, right? N was 10 because that was the 10 flights are being surveyed. Let's look at B. What's the probability that there were no more than 5 on-time flights? Now, no more than 5. Let's think about that. No more than 5. That means 0, 1, 2, 3, 4, or 5, right? Or we could write X is less than or equal to 5. Now, here's the problem. To do that by hand, I actually need to find the probability of 0, the probability of 1, the probability of 2, and go on until I get the probability of 5 and then add them all up. And that's kind of a pain in the butt. Using that formula 6 different times there, whew, that's a nasty way. But there is an easier way, and that's the calculator. So we are going to actually find the probability for part B on the calculator. I would always suggest doing those on the calculator. But I also want to show you doing probability part A on the calculator, because even though that's a relatively easy thing to do with the formula, some people are going to appreciate being able to do it on the calculator. You'll notice we'll start by redoing part A just to show you that, and then of course we'll answer part B. So we'll do A here, and then we'll do part B here. All right, let's do it on the calculator. First off, you'll remember that 4A asked me for the probability of 7. Okay, so that's what we're going to do now. We're going to use the binom PDF, which means probability distribution function, on the calculator. I'm going to try to show that in a video. All right, so P of 7 is about 0.213, and again, that is what we had on our calculator. I'm not sure how that video is going to work, by the way. It looks like you might have to play it yourself. I don't know. There might look for a play button on it, though. Sorry, it's the first video I've tried to put in here. Let's do 4B on the calculator. I'm going to do pretty much exactly, starting off, the same thing, except I'm going to get the binom CDF, which, by the way, means cumulative distribution function. It knows to look for the probability that X is less than or equal to a certain X value, which again, what we want to know is the probability that X is less than or equal to 5. Okay. I don't think I'm going to do another video for that, but again, you're going to end up with binom CDF. Then you're going to put in your N value, your P value, and the X value of 5. I'm going to go ahead and do that. Pause me down, you do it too, and then we'll check answers. All right, all I did here was I just included my calculator screen, and I'm going to show my answer there. Notice again, for 4B, when I want the probability that X is less than or equal to some value, I'm going to use the CDF. If I want simply the probability that X is equal to one value, we use the PDF. So keep that distinction very clear in your mind. It looks like about 4% of the samples of size 10 of these flights would have no more than 5 on-time flights. Which makes sense, right? Because an on-time flight, 79% of the time, it happens a lot, right? So for a sample of size 10 to get 5 or less on-time flights, well, that's going to happen pretty infrequently, isn't it? It's not going to happen often. Okay, we have seen probabilities with less than or equal to before. We had to use some complement rules or some other logic, and you're going to see that same thing here. We're also going to be able to use our CDF and our PDF binomial functions to great effect. Okay, so let's do 4C together. Okay, so we have the same setup, and we are simply finding the probability that there were at least 6 on-time flights. Okay, now you First of all, let's write it down. Probability of x is at least 6, right? Greater than or equal to 6. Now, the CDF function does not help me because that's the probability that x is less than or equal to x, and I want greater than or equal to 6, right? But I think to myself, well, how is that related to what we just did in part B? Would you agree that the events no more than 5, and let's put that in inequality notation, and at least 6, let's put that in inequality notation. Would you agree those are complements? They are, aren't they? Those are complements. That and that basically break up the possibilities, right? X can be anything from 0 to 10. Whoops. And we already found the probability that x is less than or equal to 5. Now we want the probability that x is greater than or equal to 6. So let's do 1 minus the probability that x is less than or equal to 5, which, remember that guy? That was that 4%, wasn't it? So let's do 1 minus, I'm going to go ahead and use a more accurate 0.0399. And so I'm going to do 1 minus that and get 0.9601, or 96%, right? About 96% of all of the samples of size 10 will result in at least 6 of those sampled flights being on time. That's what we're saying. Look at part D and try to do that on your own. Notice I'm talking about the probability that there are 3 or 4 on-time flights. I'll give you a hint and say there's not any one command you can put into the calculator to get that answer out, but use your imagination. Use what you know about the CDF or PDF binomial functions and see what you get. Pause me down here, try it out. All right, there's my calculator screen, but let me show it over here. What part D is asking me for is the probability that x is 3 or 4, right? And since those are mutually exclusive, I can add those probabilities. And so I do the binom PDF for, notice PDF, for x is 3, and you'll see that in the first binom PDF there. And then I do, again, binom PDF when x is 4, which you'll see in the second one. And I just, for convenience, stuck it all on one line, making sure, remember, very important here, to get that parenthesis at the end of the first binom PDF, or it will really mess things up. I also hit enter a couple times because I have those broken pixels on my calculator, so it was hard to read those. But there's my answer. Looks like about, use your approximately equal signs, remember, 0.008, which notice is 0.8%. So 0.8%, less than 1% of those samples will have 3 or 4 on-time flights. Okay, good to know. Look at E. See what you think about E. Pause me down and come back to me. Here's what I think. First of all, I want the probability that x is less than 7, right? Okay, how do I get them from what I know? Again, back up to the stuff the calculator will give me, right? The CDF gives me the probability that x is less than or equal to x. So I could find the probability that x is less than or equal to 7 with the CDF function, right? The PDF will give me the probability that x is 7 with the PDF function. Well, how do I find the probability that x is less than 7? How is that related? Isn't that equal to the probability that x is less than or equal to 7 minus the probability that x equals 7? So I'm going to do that. For the first one here, I got to do the CDF function, right? For the second one, that's the PDF. So I'm going to probably show that on the calculator. Go ahead and try that out on your calculator and we'll see what we get. Okay, so again, I did what I said I would do. Notice the minus sign there. Right, and again, I got the CDF to get the probability that x is less than or equal to 7, and then I've got the minus, the PDF, which will give me the probability that x equals 7. And of course, first two lines, I just ignore that. I just copied my answer down below. Oops, approximately equal to 0.139. So 13.9% of the samples, let's complete our sentence, will have less than 7 on-time flights. Make sense? All right. I also have some instructions here for StatCrunch. I do not, however, I don't think have the capability of showing you that, but play around with it so you understand how to do that in StatCrunch. Why don't you pause me down and answer these questions for number 5, and then we'll come back and I'll give you my answers. Notice that P is 0.07. We're back to our 7% of people have O negative blood type example. And it says now we're selecting 20 people at random. So we're talking about n equals 20. Part A is exactly, what is the probability that exactly 5 of them are O negative? Again, I rewrote that as the probability that x equals 5. And I could do this on the Binom PDF on my calculator easily enough, although I did do it in the StatCrunch as it tells me to. I went to Stat, well, I opened up StatCrunch obviously, and then I went to Stat, Calculators, and Binomial. It gave me a place to put my n in, my p in, and then it also has a spot where you can form the probability p of x equals 5. So you form that and it automatically calculates it, and of course I'm going to round it, so let me put in approximately equal sign, and that looked like 0.0088. Letter B. You know what? Let me skip letter B for now. Let's do letter C, because that's the exact same thing as A, except for I'm asking for 20 instead of 5, right? So I'm going to put 20 into my StatCrunch calculator so it reads the proper probability, and it gets something kind of crazy. Let me show you. 7.9792 E negative 24. Do you remember that scientific notation? That means take your decimal place at between the 7 and the 9 and then move it to the left 24 spots, which makes 23 zeros, right? Then that, which any normal person would be like, hey, that's just 0. So we're going to say that the probability that x is 20 is 0. Now think about that. We're going to select 20 people. What's the probability that all 20 are O negative when any one person being O negative is 7% probability? Come on, that's got to happen. So very not at all really, right? There is a slight probability, but really for meaningful probabilities, that's really 0. So we're going to call it 0. Now, for D, probability less than 15, I have got, ooh, that's supposed to be a whole, that is ugly, isn't it? Let's try that again. I'm going to put that sucker right into my StatCrunch. Changing, I had an equal sign last, I'm going to change that to a less than sign, and then I'm going to put my 15 in there. And I'm just doing it on the calculator as I get. Now look at that, equals 1. If you did it on StatCrunch, you'll see that. What's that mean? Does that mean those are the only possibilities? You're going to see if you put in the probability that x is 16 or 17 or 18 or 19 or the 20 that we just put in, those probabilities are so very small that you end up with the probability that x is less than 15 being 1. Now technically it's not 1, right? Because we know it is possible to get 16 or 18 or even 20 O negative people in our sample. It's just very, 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 very unlikely. And so you have that rounding error there. Now, to do part B, let's go back to this. The probability that between 10 and 15 inclusive are O negative. This is what I mean. Probability that 10 is less than or equal to X, which is less than or equal to 15. That's what I'm asked after. Now, the calculator does not do this probability nice and neatly. You've got to really do a lot of finagling. But StatCrunch is awesome. That's what these tabs, standard and between, do. When you get to StatCrunch, you'll see that you start off in the standard tab, but if you hit the between button, it'll give you a place to put a probability in, just like I formed there with the 10 less than or equal to X, less than or equal to 15. And I went ahead and put 10 and 15 in, and I computed that. And I did get something very, very small. I think I have the right number of zeros there. But that is what you should get. You should try to do those for your own sake. All right, in 6.1, we talked about the mean and the standard deviation of discrete random variables. Here we do the same thing, but of course we're talking about binomial distribution specifically. We could use the formulas from the last section for mean and standard deviation, but they're way more complicated than need be. Turns out that if I know something is a binomial experiment, the mean and the standard deviation formulas are way simpler. So make sure when you're asked in 6.2 to find the mean and standard deviations of these things, you use these formulas and not those in 6.1. Okay, we have a binomial experiment with n independent trials and probability of success p. So they're just setting us up. Has a mean and standard deviation given by these formulas. Remember, mu is mean and sigma is standard deviation. Those are abbreviations that we saw earlier in the semester. And simply put, the mean of the x values is n times p. Done and done. And the standard deviation of those x values is not much more complicated. We're going to take n times p times 1 minus p and then square root it. Okay? So why don't you try to use those formulas for 6a and 6b? Pause me down, come back to me. Okay, for part A, first of all, let's read this over. According to the American Red Cross, 7% of people in the U.S. have blood type O negative. That's going to be our P. A simple random sample of size 500, we've got our N here, is obtained and the number of people with O negative blood, X, is recorded. So, finding the mean, I just go mu of X equals N times P, and N is 500, P is 0.07. Multiply them together, you get 35. Now what that is 35 people with O negative blood. Again, this is the mean of the X values, and the X values are the number of people in the sample who had O negative blood. So on average, when I sample, on average, I should get about 35 people with O negative blood. If I get way more or way less, then I think, hey, wait, maybe something's wrong. Maybe I miscalculated. Maybe I did some data entry errors. Part B, standard deviation, and I've got sigma sub x equals square root of n times p times 1 minus p. So square root of, let's see, our n value of 500, our p value of 0.07, and our 1 minus p of 1 minus 0.07, right? So of course on the calculator, I'm really going to put in square root of 500 times 0.07 times doing that 1 minus 0.07 to get 0.93 in my head. I'm going to get that. And what is that? That is about 5.71. Again, that has the same units. So, on average, a sample of 500 should get about 35 people with O negative blood, with a standard deviation of 5.71. I do have this worksheet mentioned down here, and unfortunately we're not collecting it this semester, but it was to be done. So if you want to do it as additional work and practice, feel free and email me about it if you would like. Next thing we want to talk about is being unusual. Is something unusual? if I find the probability that 45 people out of this sample of 500 are O negative is about 0.015. By the way, you can just calculate that. Think about what probability I'm after, right? Was that unusual? Before, we said stuff like, well, if the probability is less than 5%, then that's unusual. Well, there is a slightly different metric to use if they ask you if an event is unusual as it pertains to a binomial distribution. So let's go to the next page for that. Okay, so in fact, it turns out that for a fixed value of p, which of course is what we are always having, right, with a binomial distribution, as the number of trials increases, the distribution becomes bell-shaped or symmetric, which basically means if n is large enough, this shape of x, the binomial distribution, will be in fact bell-shaped, which means we can go back to our chapter 4 stuff, I think it was, and use the empirical rule. Oops, sorry, that was chapter 3. And you'll recall that for bell-shaped distributions, the empirical rule told us 95% of all outcomes lie between mu minus 2 sigma and mu plus 2 sigma. So what that means is we're thinking about this. Here's x, and of course mu is in the middle, right? Here's mu minus 2 sigma, here's mu plus 2 sigma. What we're saying is that 95% of the observations of the possible values of x lie within this region, which of course if the whole thing is 100%, then that means on the tails you get 5%, right? 100 minus 95%, the middle. So we have this. The empirical rule for unusual events in binomial distributions. First of all, you do have to make sure you've got a bell-shaped curve. And so we're going to start off with, be sure that n times p times 1 minus p is less than or equal, greater than or equal to 10. Okay, as long as that is true, then we can say 95% of all outcomes lie between those two values, and so any observation that lies outside this interval can be labeled as unusual because it occurs 5% of the time or less. I love that logic. That's so cool. Okay, let's do part 7 together. 7. Again, let's look at the sample of size 500 to determine blood type. Recall, 7% of people are O negative. Simple random sample of 500 is obtained and the number of people with O negative X is recorded. First of all, A, calculate n times p times 1 minus p to verify that in fact it is greater than or equal to 10. So, simply put, n is 500, p is 0.07. Okay, and when I calculate that, I get 32.55, which is greater than or equal to 10. So that criteria is met. Now, let's find mu minus 2 sigma and mu plus 2 sigma. That's parts B and C. That will tell us between which two values 95% of the outcomes lie. Okay, so mu minus 2 sigma, using our mu and sigma from before, I got 35 minus 2 times 5.71. And again, that's the mu and the sigma that we just calculated. All right, and that's going to be exactly 23.58. Again, remember that this is a value of X, the number of people with O negative blood. Okay, let's do mu plus 2 sigma. Ooh, that is ugly, isn't it? Let's try to clean that up. Never helps you out to be messy. 35 plus 2 times 5.71. And what I'm going to do in my calculator is I'm just going to hit second enter to get back the previous command and then turn the minus into a plus sign and hit enter. And now I get 46.42. Now, part D helps us visualize what's going on. What is the interval of usual outcomes? So, it is usual to get in our sample between 23.58 and 46.42 people with O negative blood. Okay? So the question is, would we consider a sample of 500 that yielded 45 O negative people to be unusual? Well, this interval here includes 45, doesn't it? So no. X equals 45 is not unusual. It does not fall outside of the mu minus 2 sigma to mu plus 2 sigma range. That's all. Okay, now E, look at that one. If you sampled 500 people and recorded that 120 were O negative, what might you conclude? Now think about this. You're sampling, right? You expect to get somewhere between 24 and 47 people, right? Thereabouts, that are O negative. And you end up with 120. What might you conclude? There's a couple of different conclusions, and basically one is simply, well, it's random. It just happened. It's okay. That can happen. It's unlikely, definitely, but it could happen. The other conclusion, which is usually the one you go with, is that is very, very unusual. That's a lot of people who had O negative. So probably we had some data entry errors or something of that nature. There is something wrong with our sample. Or perhaps the assumptions that I started out with, for instance, that 7% of people in the US are O negative, maybe that's wrong. Now that's something we delve into a little bit into chapters 8 and 9, but unfortunately we're not going to get to this semester, but that's for another time.